Here's the key for the volume by revolutions homework. We have two functions, the square root of x and x cubed. Our square root of x is right here, and our x cubed is our solid curve. We have to write and evaluate an integral expression for the volume of the solid when S, which is right here, is revolved about the x-axis. Okay, so we're going around the x-axis, which means that our broken curve, the square root of x, is the greater of the two curves, so it will be first in our integrand. So we have that one being squared minus the lower, smaller curve, x cubed, being squared. Our integral goes from the origin, which is 0, 0, to the point 1, 1, so our bounds are 0 and 1, and we need our pi out front as our coefficient. And there's our volume. The whole thing gets a dx, since our washers have a height of just a little bit of x. All right, let me scroll up a little bit so we have a little more room here. So we now have to solve this as well, because this is write and evaluate. So let's simplify it for starters. We have pi out front, the integral from 0 to 1. The square root of x being squared is just x. X to the sixth, x cubed being squared is x to the sixth. So we're actually looking to solve this integral. All right, so antiderive. When pi is hanging out front, x turns into x squared over 2. X to the sixth turns into x to the 7th over 7. And that's being evaluated from 0 to 1, which should go pretty quickly. When we plug in 1, we have 1/2 minus 1/7. When we plug in 0, we get 0. All right, 0 over 2 minus 0 over 7. So there's our answer right there, which we can simplify. This is over 14, so this is 7/14. So we have pi and then 7/14 minus 2/14, which again is a good answer. Or we can finally simplify that to 5 pi over 14. That would be the most simplified answer. Part B, write but do not evaluate an integral expression for the volume of the solid when S is rotated around the horizontal line y equals -1. So if we go back to our graph, y equals -1 will be down here. That's below the curve, which means that we're going to keep the order of our functions, but we have to add 1 to each of them to account for the fact that we are going 1 unit below the x-axis. So our volume will be equal to pi times the integral from 0 to 1 still, and we're going to have the square root of x plus 1. Technically it's minus -1, but double negative means positive, and that is being squared. The plus 1 is not underneath the radical. Minus, and then we have x cubed plus 1. That is also wrapped and squared, and the whole thing gets a dx. And we are done because it says write but do not evaluate. Okay, for our next problem, we have another, this time the horizontal line y equals 4. Right, that line is well above our curve, our region, I should say. So since it's above, we're going to change the order of our functions, because now x cubed is further away from the line than the square root of x. So x cubed is going to go first, the square root of x is going to go second. In addition, because we have a line above, we now put the k value, the 4, it goes first. So we will have 4 minus x cubed, that's one part, and that's squared, minus, and then 4 minus the square root of x, wrapped and squared. That whole thing gets a dx, integral from 0 to 1, and pi out front of that. That's our volume. Okay, and then finally write and evaluate an integral expression for the volume when S is rotated around the y-axis. Okay, so to go around the y-axis, we need to have functions which are x in terms of y instead of y in terms of x. So our first function is y equals the square root of x. We need to get x all by itself, which means we have to square both sides, so x is equal to y squared. Our second function is y equals the x cubed function. Well, we need to get x all by itself, so we have to take the cube root of each side. So we have x is equal to the cube root of y. Okay, so now let's go back to the picture for a second. We're still looking at the same region, all right, except this time we're going around the y-axis. So because we're going around the y-axis, our little height of our washers is going to be dy. That's why we had to change everything in terms of y. The curve, which is further away from the y-axis, the in this case the greater curve, would be the solid curve, which is x cubed. So we're not using x cubed. We are using, let's get back up here, we're using the cube root of y, but that curve is further away from the y-axis, therefore it will go first. So our volume is going to be pi times the integral. Now the points of intersection are still 0, 0, and 1, 1. We're using the y-coordinates now, which happen to be the same as the x-coordinates. So it's still 0 to 1, but it could have changed had the two curves intersected at a different point. We said the cube root of y is going to go first, so that will be squared, minus, and then we have y squared, that's our second curve, and that's also being squared, and the whole thing gets a dy. Okay, we're going to simplify this. We have y to the 1/3 being squared, so this is really pi times the integral from 0 to 1 of y to the 2/3, and y squared squared is y to the 4th. Right? So we have y to the 2/3 minus y to the 4th dy. We're going to antiderive that, so pi is hanging out front. Y to the 2/3 becomes y to the 5/3 over 5/3. Y to the 4th becomes y to the 5th over 5. And that's being evaluated from 0 to 1. So that looks pretty messy, and part of it is, but it's not super messy because our bounds, 0 and y equals 0 and y equals 1, are not all that bad. Alright, so when we plug 1 into this, well, 1 to any power is 1. So 1 to the 5/3 is going to be 1. So pi out front. Then we have 1 over 5/3 minus 1 to the 5th is 1 over 5. When we plug in 0, 0 to any power is 0. Divided by 5/3 is still 0. 0 to the 5th over 5 is still 0. So this is our answer right here. Now, 1 divided by 5/3 is the same thing as 3/5. So we technically have pi times 3/5 minus 1/5, or 2 pi over